So you probably remember Ohm's law from school, right? That super simple V equals I times R formula. It feels like one of those bedrock rules of physics, kind of like gravity. But what if I told you that our entire digital world, I mean everything from your phone to the internet itself, is built on materials that intentionally, deliberately break that law? Today we're going to dig into why this so-called failure is actually one of the most important principles in all of modern technology.
So let's just get right to it and ask the big question. Is Ohm's law times always true? Well, the short answer is a big, fat no. It's a fantastic rule of thumb for simple circuits, for sure. But the most important materials in electronics, the ones that make all of our amazing tech possible, they completely ignore it. And that's where things get really interesting. All right, here's our game plan. First, we'll look at when and how Ohm's law breaks down. Then we're going to uncover the secret of something called resistivity and see how temperature can totally change a material's electrical personality. After that, we'll roll up our sleeves and run through some real-world calculations. And finally, we'll wrap it all up with a quick summary. So let's get started with the rule breakers.
Okay, so let's explore where this fundamental law starts to show its cracks. See, Ohm's law predicts a really simple straight-line relationship between voltage and current. You double the voltage, you get double the current. Easy. But for a ton of crucial electronic components, it's just not that simple at all. Now, this graph right here, this is Ohm's law in its purest form. For a simple conductor, like a plain old copper wire, the relationship between voltage and current is a perfect, predictable, straight line. You push harder with voltage, you get a proportionally bigger flow of current. It's simple, it's predictable, and for a lot of common metals, it works like a charm.
But this is where that nice, predictable path comes to a screeching halt. Because a whole class of incredibly important materials, well, they just don't play by that straight line rule. They've got their own set of rules, and it's from those rules that modern electronics was born. Whoa, take a look at this. This curve shows what happens in a semiconductor diode. It is anything but a straight line. If you apply a little bit of positive voltage, the current just shoots up exponentially. But, and this is the key part, if you reverse the voltage and make it negative, basically nothing happens. Almost no current flows at all. It's like a one-way street for electricity. This isn't just bending the rules of Ohm's law, it's completely rewriting them.
And if you thought that was weird, check this out. This material is gallium arsenide. Now just follow the curve. As we increase the voltage, the current goes up, which seems normal, but then it hits a peak. And in this middle section, as you keep increasing the voltage, the current actually starts to decrease. This is called a negative resistance region. I know, it sounds totally impossible, but this exact bizarre property is harnessed to create high-frequency oscillators used in things like radar systems. It's engineering the weirdness.
So the big question is why? Why do these materials behave so differently? Well, the answer isn't in the object's shape or how big it is. It's buried deep inside the material itself. To understand this, we need to go beyond resistance and dig into a more fundamental idea, resistivity.
And that brings us to resistivity, that little Greek letter rho. Okay, so think of it this way. Resistance depends on an object's length and thickness, right? But resistivity is a fundamental property of the substance itself. Copper has a certain resistivity, period. Doesn't matter if it's a huge cable or a microscopic wire. Resistivity is the true measure of how much a material inherently fights against the flow of electrons.
So what actually determines a material's resistivity? It all comes down to this formula. Now don't worry, M and E, the electron's mass and charge, are just constants we can ignore for now. The two variables that really matter are N and T, tau. N is the number density, basically how many free electrons you have hanging around to carry a current. And tau is the relaxation time. Think of it like this. Tau is the average time an electron gets to zip around freely before it smacks into an atom. It's kind of like a pinball machine. A long tau means the ball travels a good distance before hitting a bumper. So, to be a good conductor, a material needs two things: tons of free electrons, a big N, and a clear path for them to travel, a long tau.
Okay, so what could possibly mess with those variables, especially that collision time, tau? Well, the biggest game changer, by far, is temperature. Heating something up or cooling it down can completely transform its electrical behavior. And this formula right here is the key. It might look a little intimidating, but it tells a really clear story about how materials react when things get hot or cold. So let's break down what each part really means.
Here's the breakdown. PT is the resistivity at whatever temperature we're interested in. Rho 0 is our starting point, the known resistivity at a reference temperature T0. But the real star of the show here is alpha.
alpha, the temperature coefficient. Just think of alpha as a material's unique sensitivity to heat. A big alpha means its resistance changes a lot with temperature, while a tiny alpha means it's super stable.
And this is where it gets absolutely fascinating. Look at the graph for copper on the left. As it gets hotter, the atoms inside start vibrating like crazy. This means our poor little electrons are crashing into them way more often, which shrinks that relaxation time tau. The result? Resistivity goes up. But now look at the semiconductors on the right. As it gets hotter, something else happens. More and more electrons break free from their atoms, dramatically increasing n, the number of charge carriers. This effect is so powerful that it completely overwhelms the increase in collisions. So for a semiconductor, as it gets hotter, its resistivity actually goes down. They have completely opposite behaviors.
And then you've got these special alloys like nichrome, which is the stuff they use in your toaster. Just look at its graph. It's almost perfectly flat. Its resistivity is incredibly stable across a huge range of temperatures. And this isn't an accident, it's an engineered property. It means that a device made from it, like a standard resistor in a circuit or the heating coil in a toaster, will have a predictable resistance whether that's at room temperature or glowing red hot.
Okay, that's enough theory. How do we actually use this stuff in the real world? Let's run through a couple of practical examples to see how engineers put these formulas to the test every single day.
All right, first problem, and this one's straight out of your kitchen. We have a nichrome toaster element. We measure its resistance when it's cold, say at room temperature, and it's 75.3 ohms. Then, we plug it into a 230-volt outlet. Once it's glowing hot, the current running through it stabilizes at 2.68 amps. So, the question is, just how hot did that little wire get?
Let's walk through this step by step. First things first, we need to figure out the element's resistance when it's hot. For that, we can use good old Ohm's law. 230 volts divided by 2.68 amps gives us 85.8 ohms. Step 2, we take our temperature formula and rearrange it to solve for the thing we want, which is the change in temperature. Third, we plug in all our numbers, our hot resistance, our cold resistance, and the known alpha value for nichrome. The math tells us the temperature increased by 820 degrees. And finally, step 4, we just add that change to our starting room temperature and we get our final answer, a scorching 847 degrees Celsius.
Okay, here's another awesome application, building a super accurate thermometer. We've got a platinum wire that we've already calibrated. We know its resistance at freezing is exactly 5 ohms, and at boiling, it's 5.23 ohms. Now we stick this wire into some mystery hot bath, and we measure a resistance of 5.795 ohms. So, what's the temperature of that bath?
Well, since platinum's resistance changes so nicely and linearly with temperature, we can just use a simple ratio. This formula is basically asking, on the scale from freezing to boiling, where does our new measurement fall? We plug in our resistance in the hot bath, the resistance at freezing, and the resistance at boiling. We do the math, and we get our answer, 345.65 degrees Celsius. It's an incredibly clever and precise way to measure temperature just by measuring resistance.
Wow, okay. We've gone all the way from the limits of Ohm's law down to the microscopic properties of materials and all the way back up to real-world devices. Let's quickly summarize what we've learned and add these powerful new ideas to your mental toolkit for understanding electricity. Here are the 3 core formulas we looked at. First, that microscopic view of resistivity, which shows it's all about the number of charge carriers and how often they collide. Second, the formula that links a material's resistivity to temperature using that key alpha coefficient. And third, the practical version of that formula for resistance, which is the one we use to figure out how hot our toaster got.
And here are the big ideas to really let sink in. First, Ohm's law is a great starting point, but it is not a universal law of nature. The real story is in a material's intrinsic resistivity. Second, temperature is a massive factor, causing conductors and semiconductors to behave in completely opposite ways. And finally, by understanding and engineering these principles, we can build the incredible technologies that define our modern world.
Which brings us to one last thought. We started this whole journey talking about the limitations and failures of Ohm's law, but it's precisely by mastering these so-called failures, these nonlinear behaviors in materials like diodes and semiconductors, that we've built the entire digital revolution. So the real question isn't about what laws are unbreakable, but rather what other failures of established rules are just out there, waiting to be harnessed to create the technologies of tomorrow.